Everyone, I'm going to start 9.4, Center of Mass. So far we have considered all objects to be point masses. In this section we'll look at how to analyze systems of objects or irregular objects where forces are acting not necessarily on the center of mass. And we'll look at how to calculate that position of center of mass. Okay, so let's first consider a system of point masses ranging from I equals 1 to I equals n. In that case, the coordinate of the center of mass, this is the position vector to the center of mass, is equal to m1, r1, the position of mass 1, plus m2, r2, all the way up to our nth mass. And that's divided by the sum of all the individual masses. Essentially, the total mass is on the bottom. This is like a weighted average of the positions of all the total masses, where a position of a higher mass has more weighting than a position of a lower mass. So this can be written in summation form like this: sum from I equals 1 to n of mi ri, and then we have the sum of all the masses, or the total mass, there in the bottom. So we can write the position of the center of the mass as a position vector, like it is here, or as in coordinates: x center of mass, y center of mass, and z center of mass. And in that coordinate form, or in 1D if we were just looking at something along an x-axis, then we can apply this relationship to each of the masses, so each of these coordinate directions. So I could have written this as x if we're just talking about the x-coordinate of the center of mass. So we'd have x's here and x positions, or y or z. Now when this changes is when instead we have a mass distribution. In that case, this sum becomes an integral, and we need to integrate over the mass. So we'll have the integral from xi to xf, for example, to find the x-coordinate of the x position dm divided by the total mass. And I could write a similar expression for y and for z. Now, before we get into some theory about using the center of mass, I just want to give some notes on the center of mass. If you can see that an object is symmetric, or it has an axis of symmetry, then the center of mass will lie along that axis of symmetry, so we can make use of symmetry in these problems. Okay, I just paused to add some diagrams for the next few notes. One is that the vertical line test can be used to locate the center of mass of an irregular object. So how you would do that is take your object and then suspend it from a point so that it's allowed to move freely and it will fall into a certain position, and then hang a vertical string down in front of the object, so something like this. So then if you trace this line through the object, it will be a line passing through the center of mass. And then repeat. So now hang it from a different corner, maybe this corner, and then trace the line again. And eventually you'll have lines that cross at the center of the mass of the object. So you could try that if you have any kind of shape maybe you can draw on. Okay, the other is that the center of mass can be at any point for an object or for a mass configuration. It does not have to be a point where there is mass or where the largest mass is. An example of this is a donut. The center of mass would be right in the center, which is actually a hole, and there's no mass there. Okay, the third is that if you balance an object on a point, so again my triangle, if I could balance this from one point, I would find that it balances on, the point it balances on is on a line which goes through the center of mass. So similar to the vertical line test, you could then rotate it maybe and balance it on another point and eventually end up with lines that cross at the center of mass. All right, let's look at the theory. Okay, I have quite a lot written here, but I'll just go through and explain the concepts behind it, which is the important part. So the formula I have from the beginning of the video is the coordinate, or the position, for the center of the mass, sum of all from I equals 1 of mi ri, the position of each mass piece, over m. And I've replaced the sum of the masses by the total mass m. So let's take the derivative of that. If we differentiate that with respect to time, I have the derivative of that position. I'm going to pull out 1 over m because that's a constant. And then I have the sum of all the masses, again constant, so we can move the derivative to that position vector for each mass position. And so then these, dr by dt, are velocities. So what we get is the total mass. I'm multiplying that over here. The total mass times the velocity of the center of the mass equals the sum of all the individual masses times their individual velocities. And this quantity, mass times velocity, should remember from the last section, that's momentum. So what we're seeing here is that the momentum of the center of mass is equal to the sum of all the individual momentums of the individual mass constituents. So we get the total momentum. Alternatively, we're finding that the total momentum of a system can be found by using its total mass and the velocity of its center of mass. And we can write a similar relationship for the net force. So let's differentiate that one more time to get acceleration. So if I take the derivative again, I can still pull the mass out, take the derivative of the center of mass, of the velocity of the center of the mass, and then I have the sum of all the masses, and each one it's the product here, so the mass times the product of the derivative of its velocity for that particular point mass. So we have dvi by dt, and all of these dv by dt's I can replace by acceleration. So the total mass times the acceleration of the center of the mass equals the sum of each individual mass part times its acceleration. And so this is the important part, really, that we can use the mass times the acceleration of the center of mass. And this is the net force. So the net force for any system would be the sum of all external forces acting on the system and then the sum of any internal forces. I've written that here. But because of Newton's third law, we know that if there are internal forces, there needs to be action-reaction pairs that are in, each internal force has a reaction pair that's also an internal force, and so that makes them all cancel out since we have equal and opposite pairs, so that will be 0. So this is our net external force. So what we're finding for the system is this form of Newton's second law, which says that the net external force acting on a system equals the mass times that acceleration. So if there are no external forces acting on a system, rarely would we ever see that case on Earth, but in that case we would have the object at rest or moving at a constant velocity. And if that net force, external net force, is balanced, if the sum adds to 0, which is the more likely case, that's what we have. Newton's first law, the object is at rest or moving at a constant velocity. So this is important because it's telling us that if we can find the center of mass for an object, then we can treat the motion of that object as it's moving around the center of mass and use the velocity, use the momentum, use the acceleration of that center of mass in order to analyze the object. So that's why finding center of mass is going to be important here for irregular objects. It's also important as we look at torque and rotational motion in the next section, where we will analyze objects that have forces acting on different locations within the object. So for some geometrical shapes, we can use the center of mass has already been determined, and we can use that by looking up the specific shape in the formula and the formula for the center of mass in a table. And I'll insert a table here so that you can see some examples of this. So some of the center of masses, we can refer to those tables and then use those coordinates as we go on to calculate the center of mass. Okay, let's do some examples. The water molecule consists of one oxygen atom, mass 16U, and two hydrogen atoms, mass 1U. The oxygen-hydrogen separation distance is D equals 9.57 times 10 to the negative 11 meters. Calculate the x and y coordinates of the center of mass of the system relative to the center of the oxygen atom. Alright, so I've drawn this out for oxygen. It looks like this. We have the large oxygen atom here, for water I mean, so the large oxygen atom there, and then the two hydrogen molecules here that are 1U each, and the angle between them is 105 degrees. So since that's centered on our coordinate axis, then we can split that angle to get the angle to the x-axis. So dividing it by 2, I have 52.5 degrees for each one. Okay, so let's calculate the x-coordinate for this center of mass. So to find the x-coordinate, we're going to take m times x for each part of the molecule. So m oxygen, x oxygen, plus m hydrogen, the first one, x hydrogen plus m hydrogen times x hydrogen, so just one for each of these hydrogen molecules. And then, or hydrogen atoms, sorry. And then when we go to calculate this, to get the x coordinate, it's this component basically of this displacement here. So that's d cos 52.5. So we'll have mh d cos 52.5 plus, this is along the same direction, mh d cos 52.5 degrees. Now I've canceled out or crossed out the mass of oxygen times x oxygen because that's at our center of our coordinate system at the origin. So like any vectors, this center of mass position vector is measured relative to an origin. So make sure to always set an origin if it hasn't been done for you to have a reference to give the coordinates of the center of mass. Okay, so that's at 0, but notice when we go to put in the total mass, which I've done here, we still keep the mass of oxygen there. So there's still weighting at the origin due to that oxygen. Okay, and then 2 times the mass of hydrogen. So plugging in the numbers, we have two identical terms here, 2 times 1 atomic mass unit, 9.57 times 10 to the negative 11 meters, cos 52.5 over the total mass, 18U. The masses in atomic mass units now, it doesn't matter what the mass is as long as you're consistent with your units because they will cancel. And the same for our x coordinate. We could use centimeters, we could use meters as long as we're using the same units throughout. So I get 6.47 times 10 to the negative 12 meters for the x coordinate of the center of mass. Now, if you can use symmetry, do, because it will simplify your problem. So we could calculate the y coordinate, but we can see that when we do, we're going to get 0 because oxygen is at 0, and then each hydrogen atom is the same distance above and below that x-axis, so at the same y position, but different signs. So they'll cancel out and we'll get a y coordinate overall of 0. So the coordinates of the center of mass are xcm, ycm is this x coordinate we just found, and then 0 for the y coordinate. All right, next example. Consider an object of uniform cross-sectional area and density as shown in the figure. Calculate the center of mass for the object relative to the indicated origin. Okay, so our object looks like this, and the origin is in the bottom corner here. And so we have 4 by 10 centimeters square and then a triangle of height 4 centimeters. So here we don't have the mass. Instead, what we know is that this is a uniform shape. And for a shape of uniform density and thickness, actually what we can do is use the area instead of the mass, and I'll show you why. So mass equals density times volume, which is density times area times thickness. And then if I plug that in, I have rho AT, so this is the mass, times the y coordinate, plus rho A2T times the y coordinate. I have two terms here, one for the square or rectangle and one for the triangle. Divided by the total mass, rho A times the thickness for each mass. So if it's uniform, we have the same thickness and density. Those are constants, and notice they're in every term. We can cancel them all out. So all of these densities and thicknesses are canceled. So we have A1, Y1 plus A2, Y2 over the total area. So you don't have to do this every time. You can remember that if the density is uniform and it's uniform thickness, then our mass is proportional to the area, and that's why we can write this in terms of the area. But okay, let's write out the expression for the y component. Okay, I paused it so you don't have to watch me write it all out, but I'm going to explain each term. So for the y coordinate, as I showed, we have it in terms of the area instead of the mass. And so let's start, I'll call object 1 this rectangle. So for 1, the area is length times width, and then the center of mass upward will be at half the height, so length over 2. That one's pretty obvious, but if you're not sure, remember just to check the table that I showed, that you can look up the center of mass coordinates for basic geometric shapes. Okay, then for the triangle, we have 1/2 base times height for its area, and now we do need that chart to find the height for this triangle. So if you look up in the chart, you'll see that the coordinate for a triangle is h/3 for the y component. So h over 3, but that's from the bottom of the triangle. So then we need to add on the length, so the height basically from the bottom due to that rectangle. So we have h over 3 plus L. And then the area is in the bottom. In this step, it's just plugging in a lot of numbers. So 4 times 10 for the area of the rectangle times 5 centimeters, 10 over 2, plus 1/2 base times height. This height over 3 centimeters plus the length 10 over the sum of the areas. And that gives 6.606 centimeters as that y-coordinate of the center of mass. Again, if you need to, calculate the x-coordinate, but it's preferred that you recognize symmetry of the situation, so we can see that this is symmetric, so the x-coordinate has to be down the center line of symmetry, which is right here at 2 centimeters. So we have our coordinates for the center of the mass of 2 centimeters and 6.06 centimeters for the y-coordinate. All right, one more example. A cylindrical object of uniform density and radius r has a second circle of radius r over 2 cut out from it. Find its center of mass relative to the indicated origin. Okay, in the case where you have a uniform shape with a piece missing from it or a hole cut out, you can actually find the center of mass by subtracting the coordinates and the mass, or the area in this case, of that hole, the position of that hole. So we're going to use the area formula again because, again, we don't have the mass, but we do know that it's a uniform shape. And by symmetry, right away we can see that this is going to be centered on that x-axis, so we'll have the center coordinate of mass for the y is 0, ycm equals 0. And I've drawn it, so we have r here, and this hole that's cut out has radius r over 2, and I'll call the larger shape 1 and then the hole 2. Okay, so our center of mass now will have a1 x1 minus a2, this whole x2. Make sure to subtract the areas or the mass if you're using the other version for another question in the bottom as well. So we only want the area of the actual solid shape that's there. Okay, then we can plug it in. So pi r squared for both circles for the area. The center of mass coordinate for this shape is r, the radius. And then we have, so this is a radius r, which is actually right here, and this is the radius of the second shape. Then we have pi r over 2 squared, and then r over 2 is the radius as well, of the smaller, of the whole. Okay, so subtracting the areas, we have the larger area minus the smaller area. And then this is just a lot of simplifying, so notice that pi r squared is in every term. We can cancel all of that. So we're left with just r here. Pi r squared cancels. I have r over 2 squared times 2, r over 8. And then this is just 1, that cancels, minus a quarter. So 7r over 8 divided by 3/4. You can flip that and multiply. And to simplify, we get 7r over 6, or 7 over 6r. So our coordinates now would be 7 over 6r and 0 for the y-coordinate. Okay, let me know if you have any questions on this. We'll come back to this in our next section on torque.